All right. So yesterday's class we left off at the point where we had just defined for a a biconvex lens, what is the focus and also what is the focal plane. I'll just brush that up and also talk about how the focus is defined for biconcave also, and then we will move on to construction rays. So we had defined for a biconvex thin lens, rays of light that come from a very distant source, something like the rays from the sun, okay, as incident on the lens. And I have also said that there are going to be, although there are going to be two refractions taking place on either.
Appa,
Yes.
the camera's ulta.
The camera is upside down.
Yeah.
Oh yeah, this Alok sir had wanted to do some videos. So he had removed the camera, and when I fitted it back, I guess it went ulta. No wonder. Okay, so is that fine now?
Yup.
Okay, so and then I had said that although there will be two refractions taking place at both surfaces, we need not show it in that form when we are doing ray diagram sketches. We can show it as being incident on the pole, and then we said that somewhere in between these two, the convergence will happen. All right. So we also said that the reason why all of these rays are going to converge at that point technically is part number one, that it's a thin lens, and point number two is that the angle of incidence varies because the curvature of the slope of the tangent, actually that is the correct term to be used. So the slope of the tangent at that point and the slope of the tangent at this point being different is going to cause different angles of incidence, and those differences in angle of incidence will cause a larger degree of deviation in this case in comparison to this case. So because of that, it so happens that all of the rays will converge approximately at one point over there, and that point we define as the focus, symbolized by capital F in ray diagrams. And then we said that the distance between the lens and the focus will therefore be called as the focal length, okay, symbolized by italicized F. We also said that incident rays that are parallel to one another but are obliquely incident, somebody has just joined in with the mic on, could you please mute it, also will converge at a point, but in this case obviously the rays are going to converge not on the principal axis, so they are going to converge at a point over there. And since there is spherical symmetry, all such rays which are parallel but are obliquely incident are going to fall along an imaginary plane that comes out like this out of the blackboard, a dimensionless imaginary plane, which is called as the focal plane. So we have defined all these things. This is just a kind of a recap of yesterday's class. right. So we also figured out the property that the focal length f is going to be half the radius of curvature. This can be proven geometrically very easily, and we'll do that a little later when we look at the image formation using the construction rays. And there is going to be another focus. So this focus now we can call as the principal focus f, and obviously there is going to be another focus on this side. And like I said, traditionally textbooks use f prime or the secondary focus. How that becomes significant when we do ray diagrams, we will take that up as it goes. Now I just want to move on to how do you do the same thing for by concave lenses. Incidentally, because in this case the rays converge at a point, a convex lens is also known as converging lens. Okay, so this is another term that is used to define used for a convex lens. So you should know that term as well. Now, when it comes to a concave lens, okay, when it comes to a concave lens, you can again define it in the same way. So you start off with rays that are parallel to the principal axis and incident on the lens at different points. So you can take one like that and one like this, and although you can do the same thing at the bottom, I won't do it for the time being. Okay, so this also has its pole and its optical center. Now in this case, what will happen is you see the curve over here has a negative slope. So that means that if you draw the tangent to that curve at that point, right, it has a curve, it has a slope which is negative. You remember in the case of the convex lenses, the slope was positive to any point of incidence, whereas it is negative over here. So therefore, it's like an upturned prism, right? It's like that. So if you break down the concave lens, of course, this is a concave lens, not to be confused with the convex that I have written on top. Then you'll find the lens to be broken up into parts in this manner. Right? So you atomize the lens, you break it up, you will get it like this. And what we know is that for a prism, so I'm going to put two prisms like that, right? What we know is a ray of light which is incident on the prism on this side is going to bend like this. So similarly, the reverse will happen, the mirror will happen for that, right? It's going to be incident on this face and it's going to emerge like that. And you can also work it out by looking at this detail over here. You draw the normal, it's going to bend towards the normal because it's going from air into light. And again, at the end of that, on the other side, the normal is going to be like that, and it's going from glass into air, so it will go away from the normal, so it's going to do that. Okay, so I don't need to go over the same instructions over here, so we can just assume that that's what is going to happen. It's going to diverge. But of course, for the same reason that the slope is different, that the slope is more over here compared to over here, the angle of incidence is going to vary. So the degree of deviation is going to be lesser in this case. Okay. So and now comes the important part, which is that if you produce these rays backwards now, okay, these rays when produced backwards, um, they are going to converge at a particular point on the principal axis. And of course, because you are producing them backwards, you don't draw a solid line. A solid line is only used to indicate the actual ray that is passing through. So if you are going to indicate the path of the ray when produced backwards, you have to use dotted lines. Okay, that's a cardinal rule of geometric optics. In fact, yeah, I just wanted to introduce that term also. What we are doing now is known as geometric optics. So basically, we are using geometry properties, angle measurements, parallel properties, etc., etc. And pretty soon we will also be using triangle properties. So the point at which these rays seem to emerge from. So you see, for somebody who is looking from this side, what it will appear like is that the rays of light are emerging from this point. They emanate from that point. Okay. So this point over here is what will be known, what will be called as the principal focus. And of course, now I better change my center of curvature slightly. And there will be another focus, of course, over here, which will be the secondary focus. So that is how you define the focal length. And then, of course, you can also talk in terms of parallel rays which are obliquely incident, and then how they are going to work out. So you produce them backwards, they'll form somewhere on this plane, and again you define the focal plane for that. In case of the concave lens also, the focal length, which is the distance between these 2 points, right, the focal length will still be equal to half of the radius of curvature. All right. So because of this property of this type of lens to diverge the rays of light which are incident on them, which are parallel to the principal axis and are incident on them, these kinds of lenses are also called as divergent lenses. Okay, so convex lens, concave lens. Convex lens's equivalent is converging lens because they converge the rays of light, and concave lens are divergent, D-I-V-E-R, divergent lens, because they diverge the rays of light. Okay, so let's just take a break there and try to see if there is anything in comment that I need to talk about. Okay, Krishna is asking, aren't there two focal points? Yeah, I think I have answered that question. Yes, there are two focal points. And then Chaitanya is asking if we are doing the second focal point. No, if you notice the lens has changed. So I'm defining the focal length for convex lens, and then for yesterday we did it for convex lens. I did a recap, and then today we are doing it for concave lens. Why will you find the second focus there? Yeah, the relevance of the second focus will come a little bit later when we are talking about construction rays. So we'll pick it up at that point of time.
Do we have bio?
No, I don't know about that. Okay, so Okay, so now that we are done with defining all the different um, terms associated with these lenses, let's proceed to the point of the whole exercise, which is to understand how does image formation actually happen in a lens. And some things associated with that, including characteristics of the image, similar to what we did with mirrors in the last class. So if you remember the other day, the first day that I had introduced to you lenses, right? I had showed you the property of lenses, right? So lenses do this. Okay, so if you have a biconvex lens, the biconvex lens tends to magnify the image that you're looking at. And a biconcave lens, when kept at an appropriate distance, tends to diminish the image. Okay, and obviously if you use a combination of the two, right, and these two have matched focal lengths, so therefore what happens is that the effect of one is cancelled out by the effect of the other. Now why does this happen? So this is what we are attempting to understand. Okay, so that's what we are going to do now. And in order to understand this, the first order of business is to um, figure out how do rays of light behave when they are incident on a lens. So you might say, my God, there's going to be an infinite number of light rays that are incident on even a tiny lens. So which rays of light should I choose? You should choose those rays of light for which you're able to accurately and easily predict the results. Okay, and what do I mean by that? Well, they're simple. So let's take the simple scenario. Like everything in science, first we look at the simplest scenario and then we attempt to understand everything from that. So we'll start again with the um, converging lens, the biconvex lens. And let's keep a focal length. See, when you are and you will be expected to do this when you are asked to do ray diagrams. You would be expected to do a sketch of the ray diagram. In most cases, you will be expected only to do a sketch of the ray diagram. And it's a good idea to be able to do the ray diagram with some specific measurements in mind. Although you can do it by hand in order to avoid errors or too many adjustments later, um, it will be a good idea to keep a center of curvature distance, that is radius of curvature distance, of about 10 centimeters. I think 10 centimeters and 10 centimeters will make it 20 centimeters. Now your book width will not be sufficient. So maybe you can keep something like 8 centimeters on one side, 8 centimeters on the other side, and 4 centimeters as your focus and 4 centimeters on this side. I'll talk about it a little bit later when we go ahead. But let me attempt to finish this section at least. Okay, construction rays. So you assume an object um, usually labeled small o, okay, at some distance away from the focus. So this is kept as the focus, and this is the primary focus and the secondary focus. So what do we know about it? Well, if you take a ray of light from the top of this object which is parallel to the principal axis incident on the lens. Where is this ray of light going? What will happen to the ray of light? Yeah, it's going to get refracted towards the focus. So we know that. Okay, so this ray over here is your first construction ray, as simple as that. Okay, because I know exactly how this thing is going to behave. Now, if I take a ray of light, and this one is a slightly more complicated one, which passes from the same, which emanates from the same point, but it passes through the secondary focus. Okay, do I know where it's going? Yeah, Chaitanya is saying it's going to go parallel to the principal axis, right? So this ray goes parallel to the principal axis. Now, what helps you to decide that? That is my question. How do you know that a ray of light that is passing through the secondary focus incident on the lens is going to pass parallel to the principal axis? Yeah, symmetry argument is one, because this is symmetrical to that. But you see, you can also argue it through the reversibility of light, principle of reversibility of light. Yes, that's right. Darshan says. So if a ray of light is incident parallel to the principal axis on the incident ray, we know it's going to pass through the focus. So therefore, if there is one that is passing through the focus and then incident on the lens, it's going to come parallel. Okay. And a third ray that you can also draw is, again, knowing the property of lenses. I got very lucky today. This just kind of working out right, which is that if there is a ray of light that is passing through the optical center, okay, then because it's a thin lens, there is going to be very small amount, such a small amount of displacement of the ray that is taking place, parallel displacement, lateral displacement, sorry, that we can almost ignore that lateral displacement and say that it is going to pass undeviated. Now it so happens that all the three construction rays, now it's become a bit crowded here, so this is the first one, this is the second one, and this is the third one. So these three construction rays are the ones that I am sure about. I know exactly how these three rays are going to behave. Now, by using these three rays, I will be able to form an image of any object, of an object placed anywhere along the principal axis. And there are certain fixed positions. So you have you can place the object much further than the center of curvature. You can put it on the center of curvature. You can put it between the center of curvature and focus, and you can put it between the focus and the optical center, and then you can find out what kind of images will be obtained. So how that happens and how that works out, we will have to look at in another video. We are running out of time now, so I'll stop here.